So in these videos that you're going to be watching over 9.5 all involve something to do with alternating series. An alternating series is one where the alternating part means the sign of the terms is gonna alternate. Okay. I'm not gonna do this. Sorry. Times a sub n. Okay, so when we talk about the a sub n pieces, we're not talking about the alternating part with the positive or negative sign. We're talking about the other piece of the series. Okay, an alternating series might also start with an n plus 1 for the power or n minus 1. Okay, and that will just be determined by where we're starting for n and whether we want our first term to be positive or negative. Okay. This piece of the expression won't determine the convergence or divergence, whether I'm starting with positive 1 or negative 1 here. Okay, the a sub n's are what are going to be most important to us. Okay. What we call the alternating series test says if our a sub n's are all positive, because again, the alternating part comes from our negative 1 to the n power. Then our alternating series, whether we're looking at this version or this version. Okay. It will converge if both of the following statements down here are true. Okay. One of them is if as n goes to infinity, our a sub n's go to 0. The other one says that we have a decreasing sequence with our a sub n's. It says for all n greater than or equal to 1, but that one is a little bit flexible. Okay, there are some problems in the book that maybe we have to start at 2 or 3. But again, from that point on, if everything is decreasing, okay, and both of these conditions are met, then we'll say we know our alternating series converges. Okay, now notice it does not say here that otherwise it diverges. However, we sort of have an out with some of this, because if our a sub n's do not go to 0, then even as we're alternating signs, okay, if these guys get closer and closer to 0, even as we hop on either side of 0, positive to negative, okay, that's when we get a convergent series. Okay, but if our positive versions of those guys and our negative ones don't get closer and closer to 0, okay, then we can say my hands are not coordinating with my mouth very well this morning already. Okay, if that is not 0, we can usually say that it diverges by the nth term test. Because if we take this whole piece together with, again, with alternating signs, if none of these things are getting closer to 0 and they're staying up here alternating back and forth between something else, okay, if they're not going to 0 either, they won't be going to 0 either. Okay, sorry that I'm already all muttering this morning. So really, if this situation is not met, if that's not satisfied, then we can go straight to the fact and say our series is going to diverge by the nth term test. Okay, even though the a sub n is not the whole term, okay, because of my little scribbled dot thing up here, this is still a valid statement. Okay, if these terms go to 0 but it's not decreasing, then we have to find another test to run. Okay. So most of our alternating series tests, if they're going to fail, most of them will fail in this part 1, which is all we need to do to say, hey, this series is going to diverge. But if I pass number 1 and don't pass number 2, then I need to find another test. So let's look at the series -1 to the n over n. -1 to the n over n. Negative 1 to the n over n is an alternating series because if we were to write down the terms, it would be negative 1 over 1, positive 1 over 2, minus 1 over 3, plus 1 over 4. This would continue on forever. So if we want to do alternating series test, we take the limit as n goes to infinity of the piece that is not the alternating part, which would be 1 over n. Okay, and that goes to 0. Ooh la la. Now, when we're trying to say or prove that the n plus first term, I replace n with n plus 1, and I compare it to the nth term, some of them, like this one, we can just say that. This is going to be less than or equal to that one. Because if I make the denominator bigger, then I make the fraction overall smaller. Okay, not all of them are this simple, though, to just say. I can't always just say it. Okay, but here I've got my terms going to 0. I've got them decreasing. So I can say that my series converges by the alternating series test. By the alternating series test. If I want to look at the series negative 1 to the n plus 1 over n factorial, then if I look at the limit as n goes to infinity of 1 over n factorial, if the bottom gets bigger, then the fraction goes to 0. So we've met our first criteria. If I look at my n plus first term and compare it to my nth term, okay, again, I have a situation that's as, I'm going to say the word straightforward, as we had up above, where all we did was change the denominator of this one, and if we make the denominator bigger, then we make the fraction smaller. Okay, so now we've met the second criteria, which means we can say that this series converges by the alternating series test. If we look at negative 1 to the n plus 1 times n plus 1 all over n, and as we let n go to infinity, n plus 1 over n does not go to 0. It goes to 1. So what we can do from here is we can say that this series diverges by the nth term test. Again, we're kind of cheating and skipping over. I say cheating. It's one of those things that once we see it once, we can understand why we can make this leap. And so maybe when I get back to class next week, I can spend 2 minutes at the beginning of class. That will be easier than me trying to draw my little dot thing again that I was doing earlier. Okay, but we do not say it diverges by the alternating series test. Okay, understand that that's not why. The alternating series test says if these two things happen, our series converges. But it doesn't say otherwise it diverges. Okay, so if it doesn't meet the criteria for the alternating series test, we have to link back to something else to explain how we know it diverges. If I look at the series negative 1 to the n times the square root of n over n plus 2. If we take the limit as n goes to infinity, square root of n is n to the 1/2. On the bottom I have an n to the first. I know that if the power on the bottom is bigger than the power on top, that this goes to 0. Okay, so we've met that first criteria. if we want to compare the n plus first term to the nth term, okay, we can't just automatically say that one of these is less than or greater than the other one. Okay. We can't just say that. We would have to mathematically prove it. Okay. Your author goes through that proof. No, he doesn't. That was a different example. Let me check real quick. I'm sorry. No. If you want an example of how to choose inequalities, like what we were doing the other day when we were playing, you can see example 2 for an example of how to show this without using derivatives. Of course, that is another way that we are familiar with, especially if the function is not too ugly and nasty. We can say, well, I'm going to take the derivative of this and hope that the derivative is negative. And if it is, then I do know that I have a decreasing sequence. Okay, so bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. If I multiply the top and the bottom, I don't like that this defaults to a bigger pen. I multiply top and bottom by 2x to the 1/2 to get rid of this is a complex fraction, and I don't like those. Okay. In my work. So if I multiply everything top and bottom by 2 and x to the 1/2, the 2 and the 1/2 are gone, that becomes 1. I get x plus 2 from here. Okay. Here I get minus 2x. And all three of these pieces are still on the bottom. Okay. On the top up here, this becomes negative x plus 2. Okay. Now, 2 is a positive number. Square root of a positive number is positive. A positive plus 2 and then squared, anything squared is positive. Okay, so I would say, well, this is going to be a negative fraction anytime x is greater than or equal to 2, greater than 2. So because it's decreasing from 2 on, I can come back to my second part and say a sub n plus 1 is less than or equal to a sub n for all n greater than or equal to 2. So I have now shown both criteria for, I'm going to scribble off to the left here, to make it necessary to say that this series converges by the alternating series test. This video has gotten a little long, so I'm going to pause it, or I'm going to stop it, and then I'm going to start a new one with the next topic.